As we saw earlier, estimating limits numerically is not a reliable method and can lead us to making an incorrect conclusion about the value of a limit. Instead, we need a better way to evaluate limits. In this course, we don't focus on the precise mathematical definition of a limit, but we can still find limits accurately if we use algebra, some common known limits, and a set of rules called limit laws. To start, we'll look at two common limits that we can just assume to be known. Again, since we're not focusing on the precise definition of a limit in this course, we won't actually prove that these are true, but we can convince ourselves that they are true pretty easily. The limit as x approaches a of c equals c for any constant c. After all, c is a constant, so changing x doesn't affect c at all. The limit as x approaches a of x is equal to a. This limit is basically saying what number does x approach as x approaches a, which of course must be a. It's like asking what color is the purple coat. It's purple. Why even ask that? But we'll see that this simple limit is very useful for finding other more complicated limits. Just these two simple limits are enough to find many more limits using algebra and limit laws, which we'll look at next. There will still be limits that we can't evaluate, but we'll learn how to handle those limits later. The limit laws are a list of rules that limits follow. In math, you may have noticed a pattern that every time you're introduced to a new mathematical object or operation, you then learn what sort of rules that new object or operation follows. For example, when you learned about exponents in algebra, shortly after you probably learned exponent rules, which involved how different exponents interact and how exponents are affected by different operations, such as multiplication and addition. We'll do the same thing here with limits. I'm just going to state these rules as facts. If we wanted to prove them, we'd need to use the precise definition of the limit, which I haven't covered. For each of the statements, let c be a constant and assume that both the limit as x approaches a of f of x and the limit as x approaches a of g of x exist. Remember that the limit doesn't exist if the function approaches two different numbers as you approach from the left versus from the right, or if it never approaches a specific number. Which means these rules don't apply if the functions approach positive or negative infinity, which we'll learn more about later. The limit as x approaches a of f of x plus g of x is equal to the limit as x approaches a of f of x plus the limit as x approaches a of g of x. The limit of a sum is the sum of the limits. The limit as x approaches a of f of x minus g of x equals the limit as x approaches a of f of x minus the limit as x approaches a of g of x. The limit of a difference is the difference of the limits. These first two limit laws basically tell us that as long as all the limits involved exist, we can break apart limits of functions at addition and subtraction. The limit as x approaches a of c times f of x is equal to c times the limit as x approaches a of f of x. We can factor constants out of limits. The limit as x approaches a of f of x times g of x is equal to the limit as x approaches a of f of x times the limit as x approaches a of g of x. The limit of a product is the product of the limits. The limit as x approaches a of f of x divided by g of x is equal to the limit as x approaches a of f of x divided by the limit as x approaches a of g of x. The limit of a ratio is the ratio of the limits. And finally, the limit as x approaches a of f of x to the power of c is equal to the limit as x approaches a of f of x raised to the power of c. So the limit of a power is the power of the limit. Essentially, limits work really well with algebra. This allows us to evaluate limits of any rational or radical function.